this is work that was done in collaboration with Matt McQuinn at the University of Washington, and then more recently trying to extend with Ani, Andy, who is a graduate student at Princeton, and Mary Angela. So the basic question is just what happens if dark matter has dark electromagnetism? Can we get these plasma-like instabilities similar to what Libby was talking about for in the standard model? And in particular, what happens in this dark electromagnetism to dark matter self-interactions? And so this interaction is mediated through a vector mediator. And I'll just consider, for the majority of this talk, just the case where you have an unbroken U1, so you have just charge and mass. And these are sort of the parameters that we're looking to think about. So to start off, I'm just going to talk about what happens if you have hard scattering. And so this has been explored before, a long time ago by Ackermann. And I think it's instructive to just think about what happens with these two particle hard scatterings and sort of how they affect the charge mass plane. So the way that they did this is just by thinking about the interaction time for hard scatters in the Milky Way in particular. So they use this velocity associated with the virial velocity for the Milky Way. And they use the dynamical time of the Milky Way, which is on the order of 10 to the 8 years. And they want to compare this to the age of the universe. So they say that the average time for the dark matter hard scatter is greater than the age of the universe if you have this inequality. And then they get basically the impact parameter by saying that they want the kinetic energy to be equal to the potential energy. And then from that, they get the hard scattering cross-section as just b squared of this impact parameter. And putting this all together, what they end up getting is a constraint, which roughly is 10 to the minus 2 charge to mass ratio of the proton. And so this is basically limiting there to be no hard scatterings within the age of the universe in the Milky Way. Okay, so this is if you have these 2 to 2 like scatterings. But astrophysics, and as Libby just showed, you can get these really interesting collective effects in the standard model through electromagnetism. And so some inspiration from astrophysics is like these supernova remnants. So here I'm just showing the supernova remnant. And the mean free path for Coulomb collisions for these 2 to 2 scatterings in this object is on the order of hundreds of parsecs, which is much larger than the physical extent of this supernova remnant. So these shocks can't be mediated with these Coulomb-like interactions, and instead what's happening, as Libby discussed, is you're getting these end-to-end interactions with these collective fields. And so one such instability or shock that I'll talk about is due to these initial magnetic fields that deflect particles, and they generate these self-generated magnetic fields. And these are called filamentation or Weibull instabilities. Although there are other types of shocks and instabilities, as Libby discussed, that can generate these types of shocks. Okay. So plasma instabilities for this dark electromagnetism has actually been discussed in the literature a long time ago in the same paper by Ackermann, Matt Buckley, et cetera. But their explanation was pretty quick, maybe comes to the same conclusion 15 years later. And they say that, given theoretical uncertainties about nonlinear evolution of such instabilities, they leave this to future work. And I don't know, this is sort of still, I feel like where we are is really trying to get at the nonlinear evolution, but I'll get there eventually. But I just want to point out that this has been discussed in the literature before. Okay, so Libby kind of did a lot of work for me already, but I'm just going to I had this in my slides already. So what Matt and I did was we just tried to look at the nonlinear regime using kinetic theory. So you have this Boltzmann equation, which is telling you about this phase space density, as Libby discussed. And the accelerations in this dark electromagnetism, or in the standard model, you get from these E and B fields. And so together with Maxwell's equations, where again you sort of take these moments of this phase space distribution to connect these two sets of equations. And so what Matt and I did, and what people often do in plasma physics, is we try to treat this perturbatively. So we start with some initial distribution function, which we assume to be a streaming Maxwellian or a Maxwellian, depending on which species you're talking about. And then we just perturb it by some small delta f, which we assume to be a plane wave. And so to get non-trivial solutions for frequencies, what ends up happening is you get this linear dispersion relationship, which depends on this ugly plasma dispersion function. And to get non-trivial solutions, you need this to be 0. And so in particular, I said that the perturbation was going to be a plane wave. And so to get this instability, what you really need is frequencies that are purely imaginary. If you can get solutions like this, then you'll get these instabilities. OK, so just like a cartoon picture of what's happening with this Weibull instability. So I said there's just like this perturbing field. So you don't necessarily have to have a background magnetic field. You just have this perturbing field, and it's assumed to be a plane wave. Now if you have streaming dark matter, so say you have like a subhalo in a Milky Way, or you have the bullet cluster, which is what I'll focus on. You have this streaming dark matter, and in our plasma we have equal parts negatively and positively charged dark matter, and there's some streaming velocity. Now in the presence of this magnetic field, what's going to happen to these charges is they're going to experience a Lorentz force, and you get charge separation. Okay, so at some later time, now what has happened, due to this charge separation, you had some initial linear momentum, so you end up getting these current sheets. And so then these current sheets are going to just generate their own magnetic fields, again, by the right-hand rule. And they're going to work to reinforce this initial magnetic field. And so you have this initially perturbing magnetic field that's now going to grow exponentially according to this gamma, this purely imaginary frequency that I talked about before. And so our goal is to try to figure out what is this gamma and compare it to inverse of it to relevant timescales to say something about how fast this instability grows. OK, so the case that Matt and I considered and others have considered is the bullet cluster, which was shown earlier in the day, but OK. And this has been used to constrain self-interactions, also hard scatter self-interactions. So basically what you see is you have initially 2 clusters that have streamed through each other. And from observations of the hot gas, you see that there's this separation in the gas. And the gas has shocked, maybe through collisionless shocks in the standard model plasma. And then we get this observation of the dark matter from gravitational lensing, where we see a small offset between the stars and the dark matter, which helps us to say something about the collisionality of the dark matter. And people have done this for hard scatters, and I'll come back to that. OK, so what happens if you have this Weibull-like instability just from this cartoon? So again, pre-merger, you have 2 clusters that have gas and dark matter. There's some relative streaming velocity. And observationally, what we see post-merger, again, is there's some separation between the gas and the dark matter because the gas is undergoing these collisional shocks. What happens if you have this dark instabilities? We think what will happen is instead, these magnetic fields will cause the dark matter to very strongly couple, and the dark matter halos won't be able to stream through each other anymore. OK. OK. So what Matt and I did, which maybe is overkill, is we considered a warm plasma. You don't consider a cold plasma, so you have some Maxwell that's describing your distribution function, and so you get this really ugly linear dispersion. But what's nice about this is you can you can expand this plasma dispersion function in various limits to talk about whether or not your plasma is cold or hot. So it's nice because you're not limiting yourself to just thinking about this is a cold plasma. Okay, so the way that this is done is with this Xi parameter, which basically indicates whether the instability grows faster or slower than the thermal motion across the timescale of the instability. And so these are just the expressions. And so what we end up doing is we just do this to linear order to find that gamma parameter for how fast the instability will grow. Okay, so we do this for the bullet cluster case. And so we assume that Xi is 1. So we want to know what happens in the cold limit. And so we just get this polynomial that we solve for the gamma. And this is just the classic Weibull solution, but now just recast for this case where you have this dark electromagnetism. And so what Matt and I did was we looked at what happens with this Xi, and you can see for the bullet cluster case, there's some uncertainty on what the temperature is in the bullet cluster. So you're only marginally in the cold limit. And then we went back and we numerically solved to find the charge to mass ratio where you can grow this instability, such that you'll get this strong coupling and the two dark matter halos will no longer pass through. This is the rate required to reach saturation. And we roughly get a charge to mass ratio of 10 to the minus 13. Okay, so you can figure out where the maximum growth rate happens in a similar way. And so electromagnetic goes like this. So it goes proportional to the plasma frequency times the streaming velocity by c. And you can compare this to the electrostatic case, which just goes proportional to just the plasma frequency. And so in the bullet cluster case, if you consider these electrostatic instabilities, like two-stream instability, and so this is the case where you have small charge separation, and those perturbations grow to give you this different type of instability. This grows faster by a factor of 10 to the 2 for the bullet cluster case, but they also saturate earlier, which I'll show in a second. So this is just kind of showing everything together. So this is the hard scatter that came from Ackermann. This is if you consider this Weibull-like instability, you're getting something like 10 to the minus 14, where you have on the y-axis the charge and on the x-axis the mass. And then this is the case if you have these electrostatic, like two-stream instability. But again, these instabilities are going to saturate faster, and I'm going to show that in a second. Recent work that has been done to show that this is the case. Okay, so there are some lingering problems in my mind with this analysis, which one is gravity, and the second is nonlinear behavior. So everything that I've done has been purely in the linear regime. So what happens in the nonlinear regime? So for the gravity case, first order thoughts are just, okay, instead just limit the time for the instability to grow to be less than the dynamical time of the system that you're considering. So this is for the two different types of instability that I've talked about. Or maybe you just include an extra term in the acceleration for the gravitational field. Okay, so now for the nonlinear regime, this is just the point that I was trying to make. So this is recent work by DeRocco and Giffen, where they do these basically one-dimensional particle and cell simulations. And what I'm showing here is some normalized energy density as a function of time. And exactly what I just pointed out in the linear regime is what we see here. So they consider both, they have an electric field as well as a magnetic field. And what they show is exactly what I just said. The two-stream instability, or the electrostatic instability, grows faster than the Weibull instability, but it saturates at earlier times. Whereas this Weibull instability, or the electromagnetic instability, takes longer to grow, but it dominates the energy density at late times. So it's really the Weibull instability or the Weibull instability at late times that is giving you this strong coupling. Okay, so Will and Giffen, they use this one-dimensional PIC simulation to put constraints also on the charge to mass ratio by looking at this non-linear regime. And they end up getting a constraint that's roughly consistent with what you get from the linear analysis. But what we've been trying to do is think about more complex simulation setups and just try to think about other sort of astrophysical systems that you can probe in the nonlinear regime. So this is a video that was done for a 2D simulation, PIC simulation by Ani. So what you have is a subhalo, what we're calling a subhalo, which you see here, and it's falling in a host halo. And what you see when I turn on the video is that eventually you start to get some evaporation of this subhalo in this background host halo. This is in the frame of the subhalo. So this is in the case where you don't have any background magnetic field. Now what happens if you turn on a background magnetic field? So same thing, but now you're in the reference frame of the Milky Way, so you're going to see the subhalo moving. Now you have some background magnetic field, and you're going to end up getting these eddies because the plasma is sort of following the magnetic field lines. So the thing about this is just like to kind of show types of behavior that you might see in the nonlinear regime, and in a very exaggerated way. So these two simulations are using velocity dispersions for the Milky Way and the subhalo that are reasonable, but the relative streaming between the two plasmas is very, very high, even higher than in the case for the bullet cluster, which we think is sort of an extreme system astrophysically. So this is just some preliminary thoughts that we have, and moving towards trying to think about this nonlinear regime with more realistic simulations. Okay. So if dark matter does interact with this dark U1, these collective processes may dominate momentum exchange over these direct hard scatters. And these electrostatic instabilities do grow faster than the electromagnetic instabilities in the linear regime, but they saturate faster. And you may see strong collective effects in systems like the bullet cluster for charge to mass ratios greater than 10 to the 14, the charge to mass ratio of the proton. But we think additional simulations are required to really strongly probe the nonlinear regime for us to more robustly constrain this parameter space. That's it. Thank you.
Thank you, Akaxia. We have 5 minutes for questions. Yeah, Marios?
Yeah, so I want to ask about your work on the linear growth rates, on the stability growth rates. So Robert Lazenby did this growth of electrostatic and viable instabilities 2 years before that. So how is your work different than his?
So totally agree. It's similar to what Robert has done. I think really what we do is 2 different things, I would say. So one, Robert purely considers the cold limit, right? So when he's looking at the distribution function, he's always assuming delta functions, which makes things much nicer.
No, he does Maxwellian. He finds the zeta function that you have as well, right?
I don't remember him finding the
yeah, it's the computation is in the appendix. Yeah.
Okay. The second thing is that he does talk about the electromagnetic case, but most of the stuff that he does talk about is from the electrostatic instabilities, right? Which what we're pointing out is that yes, the electromagnetic instability does grow faster. The electrostatic instability does grow faster, but it also saturates earlier, right? And so the electromagnetic instabilities are actually going to be the thing that, as Will showed, will dominate the energy density at late times, and that's really going to be the thing that strongly couples the dark matter together at late times. So that's the other thing.
Okay, so despite him doing the Weibel as well, he said, because I'm not too familiar with the details, he said that the electrostatic is the one that dominates.
Yeah, so he mostly considers, I don't know if he says that it dominates, but he says that it grows the fastest, and so that's mostly what he focuses on, is the electrostatic case.
Yeah, so if you can go back to slide 16, where you show the simulation. Yeah, so I wanted to ask about the behavior of the red curve, to question about the red curve. So first, if there is a way to understand why it grows and then it goes down, and two, if there is like a way to understand the value of the plateau, is that like some equipartition value, the asymptotic value of the red curve, and why it grows and then goes down?
Yeah, this is a better question for Will, I think.
Yeah.
Will, do you have some sense of why you see this plateau?
Yeah, sure. I mean, that comes from when you hit the saturation for the two-stream instability. So the saturation levels are obviously in different places because the processes that are causing the saturation change. In the case of the two-stream instability, which you get...
Can you use your seat mic, please?
Hello? Hello?
It works.
Okay. Yeah, so in the case of the two-stream instability, what's causing the saturation is effectively electron trapping. So the electric field gets so large that the electrons can't continually build it up larger and larger. They sort of just oscillate back and forth in these things called like phase space vortices. But that happens at a lower energy density. And so when that happens, that basically cuts off all of the electrostatic stuff. It just sort of thermalizes. But the Weibel modes, it's a lot harder to kill a magnetic field than it is to kill an electric field. And so the Weibel modes continue to grow.
Ari? Say dark photon had a kinetic mixing with the standard model photon. Is there a way to disrupt the growth of these instabilities by the fact that there are standard model ions as well, such that you can salvage some of this parameter space again?
Yeah, exactly. So in the paper with Matt McQuinn, we actually do consider this case. We do also consider kinetically mixed photon. And in that case, for the bullet cluster, what you see is that the constraint, or the parameter space that is affected is smaller, basically because of electron-electron scattering. But you only really get like 2 orders of magnitude in charge mass relative to the proton.
That should depend on the choice of mixing and things like that, no?
Oh, yeah.